So I hope the in-class activities gave you some insight in what the proof of the intermediate value theorem is going to be like, because we're going to roll right through it. This video is for the formal proof of the intermediate value theorem. So first we're going to review a definition from the in-class activities. We're going to work through the main lemma from the in-class activities, which is pretty much the whole proof. Once we get the main lemma, the next thing is we get the intermediate value theorem as a direct consequence. All right, so let's start with what we were assuming. We have our function f, whose domain is a closed interval, and it's a continuous function. And for now, we're going to assume that f of a is less than f of b. The proof is very similar when f of b is less than f of a. And we're going to assume that d is some number in between f of a and f of b. So that means d is bigger than f of a and smaller than f of b. So here's what part of the graph definitely looks like, right? So we have f of a, we have a point at x equals a, y equals f of a, and then we have another point at b, x equals b, y equals f of b. And then here's what the rest of the graph may look like. So I'm going to put the d in there for reference. And a lot of things could happen with that function in between x equals a and x equals b. But we know, or at least we think we know, that it's going to cross d once, maybe more than once. So I have this one crossing y equals d several times. And I want to concentrate on two of those points on the graph. I want to concentrate on x equals t, which is the first time the graph hits y equals d. And I want to concentrate on that x equals s, which is the last time that the graph hits x equals d. And I want to characterize those two numbers because those are the ones we're going to be focusing on. Actually, in this video, we're going to be focusing on, I can't remember, I think it's s, and then x equals t is the one that you're going to do in the activities if you choose to do so. So if we want to characterize t, what's happening with t? Well, everything to the left of x equals t, the outputs are going to be smaller than d. And if you want to find any points, maybe you can't find them, but if you want to find any points where the outputs are bigger than d, then you have to look to the right of x equals t. And similarly, for characterizing s, anything to the right of x equals s, the function values are going to be bigger than d. And if you want to find any points where the function values are less than d, you have to look to the left of x equals s. And so that motivates the following definitions. Again, our function has a domain of a closed interval. It's continuous. And d is some number between f of a and f of b. We're then going to define the following. We're going to define the set big S being all the inputs where the outputs are less than or equal to d. And then t is equal to all the inputs where the outputs are greater than or equal to d. And then we're going to define s to be the supremum of s, right? Because if you remember in that picture that we had before, the s was the biggest one where the biggest one where the outputs were less than or equal to d. And then similarly, we're going to define t to be the infimum of big T. So here's our main lemma. If, again, our function is the same function we had before, domain is a closed interval, it's continuous, and then d is the same as before, where d is between f of a and f of b. And we're gonna look at s equal to the set of all x whose outputs are less than or equal to d. T is the set of all inputs whose outputs are greater than or equal to d. And little s is the supremum of s, and little t is the infimum of t. Then the first thing we have to prove, and this is actually pretty important because we want these things to be in our domain, s and t are both in the closed interval a, b. If they're not, that gives us issues because we can't plug them into the function. And the reason we want to plug them into the function is because f of s and f of t are both equal to d. That's going to give us the points we want for our intermediate value theorem. All right, so we're going to prove both parts for s. I'll leave the t version of the lemma as an exercise for you. It's very similar to the s version. So we're going to look at 1 first, and we're going to first note that S is a subset of the closed interval AB. And we know that B is an upper bound for S. It has to be an upper bound for S because S is contained in there, right? But since B is an upper bound for S, that means it has to be at least as big as the least upper bound. And guess what? The least upper bound is little s. And so that means that little s is less than or equal to B. Similar, we know that f of A is less than or equal to D. That means that A is actually in the set S. And then since S is an upper bound for the big S, that means S has to be bigger than or equal to A. We put those together. S has to be between A and B, so it is in the closed interval between A and B. So that wasn't too bad. So now we're going to prove 2. That one's a little bit more challenging. We're going to have to prove that one in 2 parts. The first part is we're going to try to prove that f of s is less than or equal to d. The second part of the proof is proving that f of s is greater than or equal to d, and then we'll put those two together to prove that they're equal to d. All right, but first of all, we want to just show that f of s is less than or equal to d. Well, remember, S is the supremum of the set big S, right? So by that nice lemma that we've used more than once, there has to be a sequence in S that converges to little s. That's for any set. There's always a sequence that converges to its supremum. Since f is continuous, that means that f of xn converges to f of s. But remember, each of those xn's is actually in the set S, and that means each of those f of xn's has to be less than or equal to d. That is the very definition of the set S. But since each of the terms of the sequence are less than or equal to d, that means the limit has to also be less than or equal to d. And guess what? That limit is f of s, so that means f of s has to be less than or equal to d. So that's the end of the first part of our proof. Now we've got to prove the second part of the proof, which is that f of s is greater than or equal to d. And now we're going to look at the other side of s. Well, if we can, if s is equal to b, then there is no other side of s. But that's actually not so bad, right? So if s is actually equal to b, we know that d is less than or equal to f of b. That's just by assumption, right? D is between f of a and f of b. So that means d is less than or equal to f of b. But remember, f of b is equal to f of s because we're assuming that s is equal to b. And so that means that f of s has to be greater than or equal to d. So now we look at the case where s is strictly less than b, and we're going to look at all the numbers between s and b, but not s, right? And one thing we know about those numbers being bigger than s is that they are upper bounds. They're upper bounds for the set big S, right? Little s is an upper bound for s. All those numbers in the interval are bigger than little s, so they are also upper bounds, right? And that means that we can't have any elements in that interval that are also in s, right? If that were the case, then little s wouldn't be an upper bound for s. So second thing is, notice that s is the infimum of that interval, s to b, which means that since it's infimum, there's some sequence that converges to it. So we can find some numbers, we'll call them xn, what the heck, the xn that are in sb that converge to s. And now we're going to play the same game as we played in the other part of that proof, right? We know that f of xn has to converge to f of s because xn converges to s. That's how continuity works, right? It's a continuous function. Also, we know that each xn is not in s. That means f of xn has to be greater than d. But if f of xn is greater than d, then it has to, whatever it converges to, that has to be greater than or equal to d. And since it converges to f of s, that means f of s is greater than or equal to d. So we've proved that f of x is less than or equal to d. We've now proved that f of s is greater than or equal to d. Put those two together, we get f of s is equal to d. So now we get our theorem, which is let f be a function whose domain is a closed interval, and let d be a real number that is in between f of a and f of b in either direction. Then there exists some x in the domain such that f of x is equal to d. And our proof at this point is very short. We simply let x equal s, or x equals t in the lemma we just proved. So as an exercise, you might want to try the following. You might want to try proving the theorem using t instead of s. It's true proving t, and it actually, like many of the proofs that we've done, it's a mirror image of what we did with s. And you might want to try proving the theorem when f of b is less than f of a, rather than f of a being less than f of b as we proved it. But other than that, that's the end of the theorem, or end of the proof of the theorem, I should say.